Hello. In this video, we will look at a special kind of 2D motion. We will look at motion along a circular path. In fact, let's be more specific. Let the particle move along the circle with a constant speed. We will call this uniform circular motion. To simplify things, we're going to center our circle so that the center of the circle is at the origin of our coordinate system. Now, you can see that I've drawn coordinate axes over here, but remember, the true origin of our coordinate system is here at the center. I've simply moved these aside so that they don't get in the way. Let's say that at t equals 0, our particle is at this point on the circle. We can see that it makes an angle phi naught with the x-axis. If we draw the position vector, it goes from the origin to the position of the particle. That's our r naught, which is the position vector at time t equals 0. In components, it would be x naught, comma y naught. These give the initial x and y positions of the particle. Turns out that if we call the radius of the circle a, there's a simple expression for x naught and y naught. X naught is a cosine phi naught, and y naught is a sine phi naught. We can see this if we draw a drop line from the particle's position to the x-axis. Then we see a right-angled triangle with a base of x naught and a height of y naught. Now we can apply the usual SOHCAHTOA rules and see that x naught is a cosine phi naught and y naught is a sine phi naught. Now, as time passes, the particle moves around the circle. We are assuming here that the particle is moving counterclockwise. How does the angle that the position vector makes with the x-axis change? Well, if it started at phi naught, then the new angle at some time t is omega t plus phi naught. Phi naught was where it started, and omega t shows you how the angle has changed. Notice that as t increases, the angle increases linearly. And so our position as a function of time becomes a cosine omega t plus phi naught, comma, a sine omega t plus phi naught. We sometimes collectively call omega t plus phi naught phi of t. Once again, position is given by these set of coordinates. And now let's look at the velocity. We know that velocity is the derivative of position with respect to time, so we take the derivative of each of the components. dx over dt, we take the derivative of a cosine omega t plus phi naught with respect to t, and we get minus omega a sine of omega t plus phi naught. Similarly, we take the derivative of a sine omega t plus phi naught with respect to t, and we get omega a cosine omega t plus phi naught. These are the x and y components of the velocity. That is, Vx is minus omega a sine omega t plus phi naught, and Vy is omega a times cosine omega t plus phi naught. Here are the expressions for the position and the velocity as a function of time. If we draw this out, we notice that the velocity is tangent to the circle and is perpendicular to the position vector. Now let's look at the speed of the particle. Remember, the speed is simply the magnitude of the velocity. So we apply the Pythagorean theorem and find that the magnitude is a omega. These are both constants. And so, as we desired, the particle has a constant speed. What is the significance of omega? Remember, the angle phi changes as phi naught plus omega t. In other words, omega gives us the rate of change of the angle. Thus we call it the angular velocity. This makes sense. We can see that both the position and the velocity implicitly carry this dependence on the angular velocity. And the magnitude of the velocity, that is the speed, is equal to the radius times the angular velocity. Sometimes, to avoid confusion, we will call v the linear speed as opposed to omega, which is the angular speed. So, the particle has a velocity. Does it have an acceleration? Well, at first we might think no. After all, we specified that the particle has a constant speed. Surely if it's not speeding up or slowing down, it won't have an acceleration. However, remember that acceleration, that is the acceleration vector, is the rate of change of the velocity vector. Because velocity is a vector and has both a magnitude and a direction, a change in either of those will result in acceleration. In this case, there is no change in magnitude, but there is a change in direction. And this leads to an acceleration. Let's go ahead and calculate A. We have the position as a function of time. We take one derivative, applying that to each of the components, and achieve the velocity. We take one more derivative and achieve the acceleration. If we compare the acceleration with the position, we notice that they're pretty similar. In fact, the only difference is that the acceleration has an additional omega squared, or rather minus omega squared, outside. We have seen in previous videos that velocity is always tangent to the trajectory of a particle, but acceleration can have a component which is tangent to the curve and thus parallel to the velocity, and a component which is perpendicular to the curve and thus perpendicular to the velocity. The component which is tangential is naturally called the tangential acceleration, and the component which is perpendicular to the curve is called the centripetal or radial acceleration. The tangential acceleration, at, changes the magnitude of v, that is, it changes the speed. So whenever a particle speeds up or slows down, that is caused by tangential acceleration. The centripetal acceleration, on the other hand, does not change the speed, but it does change the direction of the velocity. Let us note a few characteristics of this uniform circular motion. Well, first let us check if there is any tangential acceleration. How can we check? Well, the tangential acceleration is parallel to the velocity. So we simply need to find the component which lies along the direction of the velocity. V hat here is a unit vector that points in the direction of the velocity. And we can get it by taking the velocity vector divided by the magnitude of the velocity. But what we find when we do this dot product is that we get 0. So there is no tangential acceleration, and the acceleration is entirely centripetal. Let's look at the direction of this centripetal acceleration. Here's our expression for the acceleration, but we recognize that it is similar to the position, and so we write the acceleration is minus omega squared times the position vector. So we see that for uniform circular motion, the velocity is perpendicular to r and thus tangent to the circle, and the acceleration a is pointed in the opposite to the position vector. So it points from the particle to the center of the circle. We know that it points in the opposite direction because of the minus sign. Of course, its magnitude and units are different because of the presence of omega squared. Here is the circle. The particle is here. This is the position vector. This is the velocity vector. And this is the acceleration vector. This is why the acceleration is called centripetal, which means center seeking. It points towards the center. However, this name is somewhat misleading, since it only points to the center if the particle is moving in a circle and at uniform speed. If the particle changes its speed, or if it moves along any curve which is not a circle, the acceleration would not necessarily point towards the center. Centripetal acceleration is perhaps better called radial acceleration. Remember, tangential acceleration is parallel to the velocity. It can either point with the velocity or against it. And centripetal acceleration, or radial acceleration, points perpendicular to the velocity. That is why it only changes the direction and not the magnitude of the velocity. What can we say about the period t of the circular motion? That is, how long does it take for the particle to go around the circle once? Well, if we move in a circle, our angle changes by 2 pi, and the particle returns to the same position. So, if the angle at t1 is theta 1, which is omega t1 plus phi naught, and the angle at t2 is theta 2, which is omega t2 plus phi naught, if the difference between those angles is 2 pi, then the particle has completed 1 revolution. If the difference was, say, 4 pi, then the particle has completed 2 revolutions, and so on. But when we subtract these two expressions, we see that the phi naught cancels, and we get omega t2 minus omega t1. But if this is the time that it takes to complete exactly 1 revolution, then this t2 minus t1 is the time period, capital T. And so we have omega times t is equal to 2 pi, or in other words, the time period is equal to 2 pi over omega. How does this work out unit-wise? 2 pi is the angle measured in radians. Omega, the angular speed or angular velocity, is measured in radians per second, which makes sense. Normal speed is measured in meters per second because it looks at how distance changes with time. Angular speed is measured in radians per second because it looks at how angle changes with time. if we look at this ratio, radians divided by radians per second, we get seconds. And so the time period would be measured in seconds. So here is one of our relations for uniform circular motion. The time period, t, is given by 2 pi over omega, where omega is the angular speed. But we should also be able to figure out the time from the linear speed, v, and the distance covered. So we also have the time period is equal to the distance covered, 2 pi r, or 2 pi a in this case, divided by v, the linear speed. Comparing these, we see that v is equal to omega a, where a is the radius of the circle. In fact, we saw this relation earlier when we calculated the speed. Since a is the radius of the circle, we usually write it as capital R, and so you will often see this relation written as v is equal to omega r. What about the magnitude of the centripetal acceleration? A is equal to minus omega squared times the position vector. Taking the magnitude of both sides, we get omega squared times capital A, which we usually write as omega squared times r. And now, using our new relation of v equals omega r, we can rewrite our expression for the centripetal acceleration as v squared over r. All we're doing is solving for omega, which is v over r, and substituting here to get v squared over r. To summarize then, here are some of the most frequently used formulae for uniform circular motion. V equals omega times r. Notice that this is a statement relating magnitudes, not vectors. Similarly, t is equal to 2 pi over omega, which is also equal to 2 pi r over v. And the centripetal acceleration is equal to omega squared r, which is equal to v squared over r. Notice that if you hold omega constant and increase r, a increases. But if you hold v constant and increase r, a decreases. Whenever you have a formula that depends on two variables, always be careful about what is being held constant. Here is a sample problem. We shall now consider the answers. Through what distance does the tip move in one revolution? Well, we've been given that the radius is 0.15 meters, and so the tip will move through one full circumference in one revolution. And thus we see that the answer is 2 pi r, which is equal to 0.3 pi meters. Second question, what is the tip speed? We know that v is equal to omega r, but to properly answer this, we need to convert omega from revolutions per minute into radians per second. Currently we have that omega is 1200 revolutions per minute. To convert from minutes into seconds, and so now we have 20 revolutions per second. And then to convert from revolutions into radians, and so now we have 40 pi radians per second. Notice this conversion factor. One revolution corresponds to 2 pi radians, because if you move in a circle once, that is, if you complete one revolution, your angle has changed by 2 pi radians. And so we have omega is 40 pi radians per second. V is equal to omega r, which would be 6 pi meters per second. The third question asks, what is the magnitude of its acceleration? We know that A is equal to omega squared times r, which gives us 40 pi radians per second squared times 0.15, which is equal to 240 pi squared meters per second squared. Finally, we look at the period. We have t is equal to 2 pi over omega, which is 2 pi over 40 pi radians per second, which simplifies into 1 over 20 seconds. If this seems really small, remember that this fan is rotating at 1200 revolutions per minute, or 20 revolutions per second, or in other words, it takes 1/20th of a second to complete one revolution. This is the end of this video. I'll see you in the next.